talk about double integrals in polar coordinate. Okay, you can remember from Math 110B polar coordinate. Okay, so I'm going to, as we go along, I give you some quick review, just in time review of polar coordinate. Now look at this region over here. Okay, this region inside the circle. Okay, if you use rectangular coordinate, then it's going to be a little bit complicated to express a region, okay, and also this region also. However, if we use polar coordinate, this will be easier to express this region. And remember polar coordinate, let me give you a quick review of polar coordinate. Polar coordinate consists of one pole, this is the pole, and the polar axis. And for any point on the plane, you're going to get two coordinates. The first coordinate will be the r. Okay, that's the r. The second coordinate will be theta, which is this angle here, theta. So using these two, you can locate any point on the plane. The way that we do this, for example, what do we do with this one? For example, say 1, pi over 4. Then how do you locate this point? To locate this point over here, you will first you draw this polar axis, and then you go pi over 4 in counterclockwise direction, and then you're going to draw a ray over here. You're going to draw a ray from the pole pointing to this direction, and then you're going to measure 1. Then you can locate this point over here. So that's how you locate the point. That's in polar coordinate. Okay. So if in polar coordinate, then this circle here has this, we can express this region here inside the circle by looking at the r. Looks like the r over here is going to be the smallest r here. See, this point here has the smallest r. R is going to be 0. So R is greater than or equal to 0. And what is the biggest R this one can get? The biggest R will be over here. That will be, say, is 1, right? The radius of that is 1. So R is between 0 and 1. So R go from 0 all the way to 1. Okay. Now what about theta? The theta over here, well, theta is the angle that is between this ray and the polar axis, right? So you see the theta over here go from what to what? It can have multiple choice. You can have many different choices. However, easy one. If for this point here, theta will be equal to 0, right? So this point over here, theta is equal to 0. Okay, and then as this point here rotate, then what happens? The theta here is going to increase, and when you finish one round, theta will be equal to 2 pi. So theta will be greater than or equal to 0 and less than or equal to 2 pi, right? Okay, then you will get this whole circle. So if we use polar coordinate to express this circle, we can, this region, then we can have this and this. This one we might as those rectangle, right? Remember when we have rectangle, what do we do? Remember in the past, we had those rectangle, right? And then like that. Okay. X go from A to B, right? And then say Y go from C to D, etc., right? So we have those rectangle. This one here is actually a circular rectangle. You can think about that. See, R go from 0 to 1, theta go from 0 to 2 pi. The first coordinate of this polar coordinate go from a constant to another constant. The second coordinate of this polar coordinate here is go from constant to constant. So we think about it as a circular rectangle. Okay, the two coordinates are bounded by constant. Okay, It's a circular rectangle. This one also. This one over here, the R here is going to be between, what is it between? Between 1, right, and 2, okay? So the first coordinate, the R is between 1 and 2. And the second coordinate, the data here is between 0 and pi, because you only get half of, see that here? You only make half a circle, right? So it's 0 to pi. So you're looking at this, comparing to those rectangle, right? You see the similarity? So rectangle here's X and Y are bounded by the constant. Here, for polar coordinate here, the R and data are bounded by constant. And sometimes we call this a circular rectangle, okay? Okay, now I'm going to give you a quick review for polar coordinate. So this is a Cartesian coordinate system, X and Y. How do you convert this into polar coordinate? And how do you convert back? So to convert that, remember there's 3 equations. Actually, there's actually one more. You're gonna have also. So remember this 3. Okay, this 3 equation. R squared over here. This is a hypotenuse. Is equal to x squared plus y squared. And this x coordinate is r times cosine theta. Y coordinate is r times sine theta. So this one. So tangent theta is actually equal to y over x. Okay. So this is this 3 equation. I think is for now you want to remember this to relate Cartesian coordinate with polar coordinate. Okay, this is how they relate. Remember this right triangle. Okay. Now after this, it's not called. Okay. I just said that it's a circular rectangle. It's actually called polar rectangle. Okay, I take it back. So the right way to say that is called polar rectangle. So remember polar coordinate has 2 coordinate, right? And the first coordinate is the R. Okay. And over here you see R here. R go from A to B. Okay, the second coordinate is the data. That's the center angle data. Okay. The data over here go from this alpha to beta. Alpha to beta. This angle over here. Okay, and this is a polar rectangle. This is a polar rectangle. Okay, it doesn't look like a rectangle to you, but it is a polar rectangle. The R and data coordinate bounded by constant. Okay. And now, what do we do? Again, we're going to do the double integral. We want to subdivide that into subpolar rectangle. And if you look at each one, okay, look at each one over here. This is one particular polar subrectangle over here. And then you pick a point over here, name this Ri star, theta j star, etc. Okay. And then you will find the Riemann sum. Okay. See this function over here. Okay. What is this one? Okay. This one over here is actually, this is xi star. Remember r times cosine theta is xi, x, right? This one over here is yj star, okay, like this, okay. Oh, xij, yij maybe, okay. So this is the function value at this point. Just remember, okay, it's a function value at this point. And then multiplied by this area of this polar subrectangle, Remember last time we tried to use umbrella, right? So this is the surface, okay, the function. And then think about this subrectangle here as a shadow, okay? And when we do the integration, you use the function value at this point times this base area. So this is what it do, okay? And then it turned out to have this Riemann sum here. And after all this, and it's going to turn that into, what does it turn into? Okay, this is R times, okay, this one here is going to turn into what? That is going to turn into F, that is going to turn into a double integral F. R times cosine theta is, this is R times cosine theta. And then this one over here is R times sine theta. And what does this one here turn into? Well, the R I star just turn into R. And then the delta R is D, turn into dr, that's d theta. Okay. And then you have to think about R change from what to what. What does the R here change to? Some people might ask, how come delta AI is equal to this? Okay, now try to think this way. Okay, try this way. This one over here, this R over here, okay, is kind of like the R is going to be this R. In this case is say Ri times this times this angle that facing it, okay, which is delta theta, okay, small delta theta. So that will be this. Okay, think about that part. This arc length is about this. Okay, circle. And this kind of like a rectangle, and then you multiply by the length of this. The length of this is a change in R. So you times this change in R, so delta R. So this part over here, this is the delta AI. Okay, this is the delta AI there. Okay. So the pink one is this one. The delta I is this. And multiply is the area of this. Okay, so you got that. Now you have to think about here R. This is integration with respect to R first. R change from what to what. If you're looking at this picture, actually looking at this one, the R here change from A to B. Okay, then you put the A to B here in. R change from A to B. And then theta here change from alpha to beta. And then you put the alpha to beta here in. Okay. So that will be the double integral over that region, over this region, over this polar rectangle. That's how you do it. Okay. Okay. Now, here's the formula. So after all this, I think you just need to remember this. This is the formula. How do you change this from polar coordinate, change to polar coordinate in a double integral? So if you integrate this continuous function over a region R, okay, it could over polar rectangle region, okay, R, okay, then where R is going to be between this R over here between A and B, R between A and B, okay, and the data over here between alpha and beta, then you can change this double integral, okay, into this double integral. The way that we do it is this. Remember the x over here in polar coordinate, we just talked about that. X is what? Let me use this color. X is R times what? cosine theta, right? So that's why you have this. And what about y? Y is r times what? Sine theta. So then you have this, okay? Then what about dA? Okay, that dA over there is going to be this dA over here is going to be this RD theta. Now think about that. This one here is the area over there. Now how can you remember? So let me draw a picture over here. Actually, we have a picture over here too, down here. Okay. You see over here, I'm going to make it larger so you can see better. So you have this region, this polar subrectangle. I like that one. Okay, so this region over here. This part over here is going to be r times d theta. Okay. Remember, how do we find the arc length, right? Remember when we have a circle with radius r, when the angle over here is theta, then this arc length over here is going to be r times theta. When theta is in radian. Okay, so this arc length over here is r times theta. So because the change in the theta here is d theta, so r times d theta gives you this. The dr over here is this one. This one here is the dr. Think about that. It's a dr over here. So this polar subrectangle, you can think about it almost like a rectangle. So it's kind of length times width. Okay. So r dr d theta. So that's how you got this. Think about that. Okay. All right. So that's how you change it. Okay. So I think the most important thing, if the Riemann sum kind of get you confused, don't worry. I think the result here is this one. Okay. Then this is the one that you want to remember. Okay. So you express x and y in terms of r and theta, and then you replace the dA here by r dr d theta. Okay, and then think about r change from what to what, theta change from what to what. Okay, so maybe we should have one example to illustrate this. Okay, let's try this one. Over here we have a function. Okay, so this is a function that we integrate with. This function over a region. And what is that region? The region is the upper half plane bounded by this circle and this circle. So I'm going to draw this region. It's always helpful if you can draw it, okay? So what do I have here? This is xy plane. This upper half circle. So you're going to have, and this is the x squared plus y squared equal to 1, the upper half circle. And x squared plus y squared equal to 4 is the other one. So that will be, so this is x squared plus y squared equal to 2 squared, like that. And then the region is between them, right? This is a region that is between them. This one here, is this a polar rectangle? Do you think it's a polar rectangle? Yeah, it is, right? Okay, let's write down the polar rectangle over here. So R is going to be between what and what? What's the smallest R? 1 and 2, right? R between 1 and 2. Okay, good. See the R here, this is 1 and this is 2, right? So the R change from 1 to 2. Okay. And let's think about also theta, the theta. Theta between what and what? Theta is the center angle. Theta, if it's here, theta will be equal to what? 0, right? Theta is going to be 0. And if it's here, theta will be what? Pi, right? So between 0 and pi. So indeed, this is a polar rectangle, okay? So that's the polar rectangle. Polar rectangle. Okay. All right. So we have this. All right. Oh, Also, the y is going to equal 0. Okay, good. Then, okay, without looking at the book, okay, see if we can do it. Okay, so let's write down this double integral 3. Okay, this is x squared plus 4y squared dA over that region R, over this region R. Remember, equal to okay, what do you replace the dA here by? What? By R what? dr d data. Okay, dA here by this. Now that will be the integral with respect to R and then with respect to data. You want this to be in terms of R and data. How can you express that in terms of R and data? So that will be, okay, let me write that down. So that will be 3. What can you replace this x by? Yeah, x is R cosine data, right? So R cosine data. Okay, and then you square this. Okay. There's no square there before. Sorry. Just checking. You pay attention. Good job. Okay. Okay. All right. So, yeah, there's no square over here. Thank you for finding this out. There's no square over here. Okay. Okay, good. Nice. Okay, I'm going to make this smaller so that I get more space. Okay, so, and then here we'll have 4. And then what do you replace this y here by? Y is equal to in polar coordinate? R times what? Sine data. Okay, now this one has a square there. Okay, good. Okay, not too bad, isn't it? So once you get the hang of it, that is not too bad. Okay, and then R here change from what to what? 1 to 2, right? Okay, so R change from 1 to 2. And then data here change from what to what? 0 to pi, right? 0 to pi. Okay, good. And you just finish. You just set up your first double integral over polar coordinate. Okay, for this polar rectangle. Okay, good job. So it might look a little bit complicated at first, but once you get a hang of it, it's not that terrible. Okay, so that is replace the dA by R, dr, d data, and you try to express x and y in terms of R and data like this. Okay, and then the rest over here, just follow the integration method, and then you can get the result. Now, for all this type of problem, a lot of time you probably need to use a half angle formula. Remember the half angle formula, right? The sine square is 1/2, 1 minus cosine of 2 data. And just for information, what's cosine square data? The half angle formula. 1/2 what? Anybody remember? 1 plus, yes, 1 plus cosine 2 data. Yeah. So these two are called the half angle formula. So when you do integration, a lot of time you use these two formula. Okay. So we were able to set up this integral, and then all we had to do is just follow the integration and get the result. Okay. I think it's most important is to know how to set up the integral. Okay, let's look at the second example over here. Find the value of the solid bounded by this plane and this paraboloid. This. Okay. So what is it? This paraboloid. A lot of time people would like to visualize it, right? Okay. Let me see if I can find a picture. Oh, it's right here. See, like this. So up here you have a paraboloid. Okay, let me label this. This one above here is z equal to 1 minus x squared minus y squared. And the one below is going to be down here is z equal to 0, right? On the xy plane. And what's our goal? Our goal here is to try to find the value of this solid. All right, so how do we do this? Okay, let's try to do it without looking at the book, okay? So the value over here is the double integral of this function, right? Is this function. This is a function that we have. Okay, let's just write it down. Function over which region? Over this region D, right? This region down on this plane, over this region D. So that is the value of that solid. And now let's change this. Okay, let's change this into, well, the function right here. What do you change the dA here with? dA with what? dA here by what? R, dr, d theta, right? Okay. And now you want to express this function in R and theta. So what do we have here actually? You have this is 1 minus x squared plus y squared parenthesis. Do you guys remember this? X squared plus y squared is actually what? In polar coordinate, it is what? Do you guys remember this? Right? This is R, this is X, and this is Y. So x squared plus y squared is equal to what? R squared, right? So that's equal R squared. So this is R squared. So it might be more direct to replace x squared plus y squared equal R squared. Okay, you don't have to go R times cosine theta, R times sine theta. Okay, so we're going to put this as 1 minus R squared. Okay, now we're almost there. Okay, all we have to do is just figure out R change from what to what. R change from what to what in this case? Looking at the picture, what's the smallest R in this region? 0. Yeah, the smallest R here will be 0, and the biggest R here was what? It's 1, right? This circle here, if you set z equal to 0, you get x squared plus y squared equal 1. So the equation for that circle over here is actually x squared plus y squared equal to 1. So the radius is 1. So I'll go from 0 to 1. Okay, good. Okay, let's figure out what the data here change from what to what. Data change from what to what? Yeah, it go one round, right? So 0 to 2 pi. Okay, good. 0 to 2 pi. Maybe I should use a green color. 0 to 2 pi. Now after this, the rest here is just routine. Okay, and then you can find the integral here.